I'm sure it will more than double.
Oh, okay, it's 2:02 now. I think we can get started. So hello everyone, welcome to ASIC seminar series. This is John, the seminar coordinator. I hope you had a great summer. And this is the kickoff of our seminars in the fall. And we have wonderful lineup of the seminars in the fall. And Kathy has been working on this. So I will need Kathy to give you a preview of our fall seminars. Kathy?
Yeah, thanks, John. And thank you everybody for being here today. It's always really exciting to start a new semester of seminars. I sent out everybody an email last week, so you've probably already seen this. Yeah, I just wanted to highlight a couple of the speakers that we have. So we will be having 4 in-person talks that's throughout the semester. So on the email that I sent, which is also, the schedule is also linked on all of John's seminar emails. You can see all of the in-person seminars, and there's 4 of those. We have some UMD people, we have some GPM people. We tried to pick a variety of speakers across a variety of disciplines. We have some AGU fellows, we have the distinguished professor from Brown. So I just want to really encourage everybody to take a look at the schedule, see if there's anything that's interesting to you. Of course, we always have the recordings available on YouTube as well. So if you can't attend something live, you can attend it later. But today we are here to talk to Dr. Baublitz. So I'm just going to go ahead and pass it to Russ to introduce her.
Okay, it's my sincere pleasure to introduce Colleen Baublitz, today's speaker. I will keep this short in the interest of time. Colleen graduated with her PhD from Columbia in 2021, and believe it or not, I attended her dissertation defense, Variability in Tropospheric Oxidation from Polluted to Remote Regions, with Arlene Fiore. And I attended because, well, it was in 2021 during the pandemic. And Colleen has been, and it was a great defense. And I told Colleen, don't worry, I'm not going to ask you any hard questions. Okay. Okay. Colleen has done great work on OH and oxidation capacity that you will hear. She is now at the EPA, who I know from our practice is hiring. Colleen, oh, and before I say Colleen, take it away, what we're going to do today is the normal mode of Colleen will speak for a period of time. We ask you to hold your questions. You can ask questions by, preferably the video and unmuting or in chat. And then I will also hold a follow-up meeting at 4 p.m. on my own Zoom channel for continued discussion. But please stick around and ask questions after Colleen's talk. Okay, Colleen, take it away.
Okay, thanks so much, Ross, and thank you so much for having me. I'm honored to, be here with you all and, to kick off the seminar series. It's really exciting. So I'm going to go ahead and share my screen to start my presentation. Okay, I think that you all should be able to see it, but certainly let me know if you can't. Okay, so thanks again for joining. I'm going to be presenting on our work trying to infer subglobal variations in tropospheric oxidation. And I know that might be somewhat jargony to some folks in the audience, so I'll talk a little bit more about what that means in the next few slides. And broadly, I think the angle with this is to help improve projections of atmospheric composition and climate. The beautiful picture that I have in the background is a photo from the NASA Atmospheric Tomography ATOM campaign, which is the main data set that I used for my PhD work, which is sort of the main focus of my talk. Okay, so I'm just going to start us off with an outline, give you a sense for where we're headed. I'm so sorry, I just got a message and it took my attention. Okay, first starting off with some motivation, what we might need to advance our understanding of the methane lifetime, as well as model representation of the primary atmospheric oxidant, the hydroxyl radical or OH. We'll discuss, our application of a recent, very comprehensive aircraft campaign known as ATOM, where we attempted to essentially develop a new proxy for OH and tried to use that proxy to learn more about what could be driving OH spatial variations, in particular in the regions that ATOM sampled. And finally, I'll discuss some work that has been happening sort of in parallel that shares a common goal with us that has been using satellite retrievals and their nice applications of those praxes to learn more about the relationship of OH with some climatological features as well as air quality. So just starting off, we're kicking off with some background here to hopefully help motivate your interest in this topic. So I'm going to, frame this in terms of OH's relationship to methane. So here I'm showing the monthly methane mole fraction from about 1985 to present. We can see from this that the methane concentration has increased substantially over that time. We are interested in this because methane is the second most influential anthropogenic greenhouse gas, and it contributes to air pollution via ozone formation. And OH is critical to linking methane and ozone, as I'll discuss in a few slides. We can see here, that there was a bit of a relief period, as Ross quickly pointed out, even just from the outline of my talk, between roughly 2000 and 2010. And I think at that time there was some, potential optimism that we may be doing well in terms of methane or reducing methane into the future. But since that time, we've seen really an accelerated increase in methane year to year. So where OH enters this methane picture, certainly as we have a concentration which reflects the balance of sources and sinks, we need to understand both those components of the equation in order to get a better sense for what might be driving these methane increases, and ideally to try to mitigate methane. So I will be focused on this sink side of the equation. So this slide, I know there's kind of a lot happening here. This slide is broadly showing the budget of methane broken down between sources on the right side and sinks on the left. I think that the main thing that I want to emphasize here is that we can see in the sink portion of the pie that tropospheric OH is represents the vast majority of the methane sink. So it's crucial that we understand this well in order to get a better sense for methane trends. Beyond that, in recent years, this has become more and more relevant. Here I'm showing, year-to-year changes and generally increases in methane. And we can see that from 2019 to 2020, at that time, we saw the highest ever recorded increase in methane concentration. And this was despite lockdowns for COVID-19. For those in the air quality community, you'll recall, and maybe you have contributed to work showing that, we saw generally widespread decreases in air pollution or air pollutants as a result of lockdowns that decreased anthropogenic emissions. But, in contrast, the story was essentially the opposite for methane. And, where OH enters this picture is that more recent work has shown that over, half of the 2019 to 2020 change in methane could be attributed to a decrease in the methane sink, or OH, from lockdown related emissions in nitrogen oxides. So this, I think helps us, helps get a hint at this air quality climate connection between OH and methane. We generally, what we know of OH, we have generally inferred on a global annual average basis. And that's done using generally ozone depleting substances that are very well regulated under the Montreal Protocol. Here in this slide, I'm showing annual concentrations of methyl chloroform, which is, one of these ozone depleting substances. And so, with our mass balance equation, where we have, concentration as it relates to emissions and losses, we have observed concentrations and very well regulated emissions. Generally, we think, right? And so, with those two terms understood, we can learn more about the losses of methyl chloroform, which largely relate to year-to-year changes in OH. And so that's, how we've learned more about OH over time. And again, this is on, a relatively coarse scale, this global annual average basis. With that being said, there is more to learn from there. in this figure, I'm showing inferred year-to-year changes in methane emissions. And so, this inference requires, some assumptions about our OH concentrations. So there's a few different lines on this plot. I'm just going to ask you to focus on the green ones, which reflect the global changes in methane. And so the dashed line represents our best estimate of OH concentrations, where the solid line is essentially using a fixed estimate of OH, and we can think of the difference between these two lines as some degree of uncertainty that we have in the OH concentration. And we can see, for some periods of time in recent decades, that this level of uncertainty that we have in OH has led not just to very large, can lead to not just very large changes in methane emissions, but also sometimes a change in our understanding of the sign of year-to-year changes in methane emissions. So certainly that is quite challenging, if we are approaching this from a mitigation perspective, where, we'd like to know, is methane increasing or decreasing? And ideally, what, at a much finer scale, what kind of sources could we look to try to better control methane? So, broadly from this, we can see that the attribution of recent methane trends is hindered by uncertainty in OH. Okay, OH, in addition to its relevance for methane, it is also very important for atmospheric chemistry, and in many ways connects atmospheric chemistry and climate across a variety of spatial and temporal scales. So I'm going to just sort of orient you to the relevant scales of interest for some of the parameters that will be influential in this talk. So on the y-axis, I have, distance in space, going from something as small as a point scale up to global. On the x-axis, I have time from seconds all the way to years. And so on one end of the spectrum, very small scales, we have OH, which we, generally can observe using field scale studies, like, for example, aircraft studies. On the other end, we have methane, which is globally well mixed and has a lifetime of roughly 10 years. And in the middle, we have, many different air pollutants, which often, have a level of variability that is relevant for example, for a chemical transport model grid cell size, or also, an urban or a regional scale. So these could include nitrogen oxides or NOx, ozone, O3, or formaldehyde, HCHO. And so OH, has a lot of influence over both these air pollutants and methane, and in many ways, OH is influenced by these other parameters too. And so, we want to think more about how they relate to one another and how these scales can be influential. Broadly, one really large takeaway, that I would like to emphasize here is that the OH lifetime is very short, on the order generally of 1 to 2 seconds. And that precludes the development of a representative measurement network. So essentially, if we had, an OH measurement in North Carolina, where I am, and in Maryland, where I imagine many of you are, that, the distance in between those, we wouldn't be able to know very much about OH through those measurements, because the lifetime is so short that they can be independent of one another. So, in lieu of that, we have to try to learn more about OH variability through its relationship to these other compounds. So I want to discuss a little bit more about what the lack of OH measurements means, and what sort of implications that has for, different products or our understanding of atmospheric chemistry and climate. And so here I am showing a figure from a paper that was led by Julie Nicely, who I believe is an alum of the University of Maryland PhD program, and also is a NASA Goddard scientist, who was such a lovely collaborator as well on my PhD work, and I really appreciated that. So here, Julie is using a variety of different chemistry climate models to essentially show the annual average methane lifetime, which is what's shown on the y-axis. We anticipate that much of the variability in the methane lifetime is due to OH as opposed to changes in methane. I just mean for that to say that the differences that you see between these models is likely, there's likely a large influence for OH in a relative sense in terms of that term. So these models, this is from the Chemistry Climate Model Intercomparison Project. These models are run with the same emission scenario or the same chemical inputs. And we can see that even with that, there's broad differences across these models in terms of both the magnitude of the methane lifetime that they represent, as well as their trends, which suggests that, the methane lifetime and probably OH are responding differently, even given the same chemical inputs. So, from this, I'm hoping to demonstrate that, we see some, some challenges to constraining these chemistry climate models because we have very few OH measurements in terms of, what we might like to use to try to get a better representation of these processes. And we can see that, in closer detail for well, I shouldn't say in close detail, but here is just essentially another example of a study that is trying to parse differences between models in terms of the sensitivity of OH to different drivers. And so here, these are showing the two plots are two different models. And the x-axis is showing different drivers of OH variability, with the y-axis being the contribution of that term to variance in the OH concentration. And so we can see, essentially broad differences between just these two example models. On the left, we see a large influence for humidity in blue, for example, and on the right, in contrast, we see a much larger influence for nitrogen oxides or NOx. We see broadly these large differences in terms of how these commonly used models are representing the sensitivity of OH even to the same inputs. So certainly more observations or a better understanding of OH variability would be really helpful in terms of pinning down what should be in our models. So, broadly, the goal of our work in this talk is to look for a new proxy that ideally could leverage satellite data in order to offer, new model constraints on OH trends, variability, and its sensitivity to its drivers. So in order to go in that direction, I'm going to give, hopefully a very simple view of, OH chemistry in terms of just some very large scale assumptions that we can make about influential parameters for OH variability. So OH cycles quickly with the hydroperoxy radical, or HO2. Its loss is mediated and generally through reaction with reactive carbon species as well as methane. And so here I have just some, some of the leading contributors to that, including formaldehyde or HCHO and carbon monoxide or Cl. And then its production can be through the reaction often of reactive nitrogen species such as nitrogen oxides or NOx, as well as ozone, O3. And actually its primary production process, I suppose, depending on where you are in the troposphere, but we think probably on a global average basis, this is the case, is through the photolysis of ozone in the presence of water vapor. And so these are just, I'm just hoping to orient you to some large scale features of OH and its relationship to these other chemical terms. And so many of you, may be aware that many of these terms we now have, in some cases, several decades of satellite retrievals available that we could try to apply to a new potential proxy for OH, and that'll sort of be our goal. And we have, faith, or we're hopeful that we might be able to find something that could serve this purpose, in part because there are some recent studies that have demonstrated the strong potential for this, or the utility of this approach. And so here I'm showing this is based on aircraft observations from the ATOM aircraft campaign. These are column concentrations of formaldehyde on the y-axis and column OH scaled by formaldehyde reactivity on the x-axis. And so these are, measured values from the ATOM campaign. And so we can see from this that formaldehyde is a relatively strong predictor of OH concentrations, and in particular on a tropospheric column basis, which is especially relevant for satellite retrievals. So, we take from this optimism that we may be able to develop, other proxies that can be useful for inferring OH variations on a smaller scale than the global basis or hemispheric basis. Okay, and so for the next part of this talk, I will be discussing how we approached using the essentially uniquely comprehensive ATOM aircraft campaign, which I've mentioned a couple times, and I will show a little bit more about in a couple of slides here. We are attempting to develop a new OH proxy, and ideally we'd like to apply that proxy to learn more about what could be contributing to OH spatial variations. Okay, so I'm going to reference back to that chemistry that I showed in the last few slides, just to frame the OH proxy that we develop and eventually evaluate for the study. And as a spoiler, I'm showing you essentially what the format of the proxy is at the bottom of the slide. So first we have OH production, which we are taking as somewhat of a simplified form of the full set of potential reactions that could go into OH production. But again, we are trying to just capture, large scale features of this variability and ideally to use terms that could be retrieved from satellites. So here we've included these two production pathways, essentially the photolysis of ozone in the presence of water vapor, as well as the HO2 and NO reaction. And then we take, essentially the largest global destruction pathway for OH, which is its reaction with carbon monoxide, and use that as our loss term for representing variability in OH loss. Okay, so the way that we look into this is using aircraft observations as well as chemistry climate model simulations. So on the left, I'm showing flight tracks from the NASA atmospheric tomography ATOM aircraft campaign. This campaign flew once per climatological season between 2016 and 2018 along, the tracks that, are shown here. And I'll just mention that in addition to the horizontal flight tracks that you see here, the plane also flew up and down vertically to get a very nice sampling of the remote troposphere. And then on the right, I'm showing, just mentioning more so the model that we use, the GFDL AM3 chemistry climate model. We have this model simulating atmospheric chemical diagnostics on an hourly basis, and then we sample the model along the ATOM flight tracks. We screen for parcels that could be influenced by fire, as gauged by CO, for stratospheric influence as gauged by water vapor, or for high solar zenith angle. And that last one is, largely because we know OH is so sensitive to sunlight, and so that could affect some of the relationships that we see on a much broader basis. Okay, and just to sort of emphasize, why we think these regions could be the regions that ATOM sampled, or the data that ATOM collected could be especially useful, in particular from our, on a modeling basis. Here I'm showing results for OH concentrations across a series of commonly used chemistry climate models. And so I have pulled out, just one example region where, these models show really broad differences in terms of the representation of OH. And so, we are hoping that we might find a proxy that can help to better characterize, why these models might be diverging in this particular region. Okay, so the way that we went about assessing the extent to which this proxy reflects variability in the OH concentration. And I'm just going to take, sorry, I should have mentioned this earlier, but just to take a quick step back to say ATOM is a very unique campaign from the perspective that it collected an extremely comprehensive suite of different parameters relevant for oxidation chemistry. And this is, essentially this campaign offers a unique opportunity to both have available direct measurements of the OH concentration, as well as essentially its key drivers. And so this is really just such a wonderful data set that we're very lucky to have available to be able to get at this question. Okay, and so back to explaining what we're doing here, what's on this slide. So broadly, this subplot is showing a 20-degree latitudinal by 2-kilometer altitude swath over the Pacific Ocean. The x-axis is our proxy, which again we have developed exclusively using the aircraft observations, as well as some rate constant terms that are well known. Then the y-axis is the direct observations of the OH concentration. We use a Bayesian regression to try to assess the extent of correlation between the proxy and OH. And the aircraft measurements for that are shown with the blue dots. The Bayesian regression is helpful because it sort of accounts for the uncertainty of the different measurements that are used as part of our proxy calculation and for OH, and that potential range is essentially in the regression is shown as that white polygon in the background. We attempt to use sort of an analogous approach for the model to the extent possible. So we have like a mixed effects model that we use to calculate the regression in the model. And so the model has, what we have for our model is output essentially all of the diagnostics that are necessary to calculate the proxy, as well as outputting the OH concentration. And so we try to have as close of a comparison between our model diagnostics and the observations as possible. And really what's, I think the most relevant, or what I would ask you to focus on for these slides, is the background color, which shows the R-squared correlation coefficient between the proxy and the OH concentration. Okay, and so we do this, essentially across the remote troposphere to try to see how well the extent to which the proxy offers predictive skill for the OH concentration. Okay, and again, just asking you to focus on the background color. Some fun animation. Okay, and so here I fit that subplot that we were just considering into a broader grid of subplots that we're using to consider this the extent of proxy skill, in this case across the Pacific. So hopefully this sort of gives you a sense for what each of these subplots is doing. Okay, and so we do this both for the Pacific and for the Atlantic basin sampled by ATOM. And so we can see that the proxy broadly covaries spatially with the observed OH concentration. Generally, the R-squared correlation coefficient is north of 0.5. So we are interpreting this to mean that the proxy may offer some useful information about what each of the terms contributing to the proxy is doing in terms of its role in OH variations. Okay, and so broadly, with our goal of identifying a proxy that could reflect these smaller scale OH variations, here I have just sort of plotted for visual comparison the direct OH concentrations in each of these bins, this time across both ocean basins. This includes essentially all the ATOM measurements between 60 south and 60 north on the left. And then on the right, I have the inferred OH concentration based on the proxy. And so we can see that the proxy is broadly reflecting spatial variability in what the ATOM campaign directly measured. Okay. And again, we are using some terms that are either measured directly or may soon be inferred using satellite measurements. Okay, and one other aspect of this proxy that we, believe can be useful is that this proxy comprises terms that relate to processes controlling OH variability, so that we might try to decompose this proxy in order to learn more about what each of those terms is contributing to variability in the OH concentration in different parts of the remote troposphere. So in this plot, I have, essentially our full calculation of the proxy on the y-axis. On the x-axis, I have the proxy with a slightly modified version of the calculation. I've held water vapor constant here. And again, this is, similarly a 2-kilometer altitude by 20-degree latitude bin. So we can see that, by holding water vapor constant, we affect the variance in the proxy. In particular, it seems at the high end of the distribution for the proxy. And so we can compare, these two or regress them essentially to infer, to what extent water vapor is affecting variability in the full proxy. And so, again, we can do this across the full extent of the ATOM measurements to try to get a sense for how these different terms are influencing spatial variability in the full proxy. So, here we can see where this example subplot fits into the broader picture of the full extent of the remote marine troposphere or ATOM sample. And we can conduct this sensitivity analysis across all of the drivers that contribute to the proxy variability to assess which might be most influential. And, we infer, right, influential as well over OH variability. So in this plot, or in these plots on the left, I have the ATOM observations. On the right, I have the model that's sampled along the ATOM flight tracks. And I've just pulled out which of the terms emerge as most influential based on that score that I mentioned in the last slide. And for terms that are much more influential than the rest of the terms, and I, infer that based on a larger, difference in R squared than 0.2, I've indicated that, but with an asterisk over that box. So we can see, from the observations that we have a large role for water vapor in terms of the proxy variability, in particular in the mid-troposphere, as well as a somewhat substantial role for nitric oxide in the upper troposphere. And in comparison, we see for the model that there may be some overemphasis in terms of the role of nitric oxide. As well, the model seems to have a little bit of a harder time capturing the key drivers in the lower troposphere. It also seems like it may be a little overly simplistic in comparison with what we see with the observations. And, one aspect of this is that there is a difference in temporal scale. The model is on an hourly basis and the observations are, on the order of 10 seconds. So that's something to consider. But, from this broadly, we can see some large scale features in terms of the prominence of different variables over the proxy, the full extent of proxy variability, and some differences between our chemistry climate model and the observations. And just to try to contextualize this with, other, sort of related studies. So here, this plot is from another paper coming out of the ATOM science team. So here, the authors ran essentially a base case box model for the methane loss rate, which again, just to remind you, is largely driven by variability in the OH concentration. And in comparison with on the y-axis, we can see, sensitivity cases where either temperature and specific humidity were held constant. And so we can see much greater spread in terms of the representation of the methane loss rate when specific humidity. Oh, I'm so sorry. I think I misspoke. It's not that they're held constant. It's that the model is run with the ATOM observations as opposed to what it would, natively represent there. And so we can see when using the when we use the observations directly, we essentially strongly affect the methane loss rate. And in particular, it seems that specific humidity is especially influential over their representation. And so that, seems to broadly be in alignment with our finding that water vapor is rather influential over proxy variability in this region. So this is, this plot is from that same paper I mentioned earlier that Julie nicely had led. And so broadly, so this is, so in her work, she developed a neural network across a variety of these chemistry climate models participating in this intercomparison project in order to represent, in order to have a sense for what broadly these models were showing in terms of their sensitivity to differences in their fields for that have influence over the methane lifetime. And so on the left, we're seeing essentially the trend in the methane lifetime per decade, and on the right, we're seeing interannual variability. And so we can see, when different inputs across models are fed into this neural network, that broadly water vapor seems to be influential in terms of the decadal trend and the methane lifetime. In addition, we also see an influence for other species related to anthropogenic pollution, in particular in terms of the interannual variability. And so those include some terms that contribute to the proxy variance as well, which are, it seems NOx, CO, and ozone. Okay, and so just to quickly summarize some broad takeaways from this project, we found that we attempted to develop a proxy that would reflect remote tropospheric OH concentrations on smaller than hemispheric scales, which is more conventional. And we attempted to apply that proxy to learn more about what could be driving spatial variability in the OH concentration. And so, broadly, our results emphasize the need for evaluating water vapor model distributions. And this also is, I believe, a point that Julie makes in her paper, but, we have strong confidence in terms of the increasing water vapor trend as a result of global temperature increases with climate change, but it's not necessarily as clear, how much that could affect OH into the future, and ultimately how that will feed back onto methane. And then broadly, I think that this approach could be applied to evaluate machine learning models for OH. And there's been some excellent progress made recently in developing other proxies based on machine learning approaches. And I'll talk, a little bit about some high-level takeaways from those papers in the next few slides. Okay, so as I mentioned, I will attempt to, give some, give just like a very high level overview, or, just some results that I think are, relevant and, that I found really interesting about some other work that has been going on in parallel related to these subhemispheric proxies for OH. Okay, so there have also been some really nice machine learning approaches for inferring OH. And, I think it's noteworthy that while, we all have, pursued these proxies somewhat separately, we come to conclusions that involve many of the same drivers. And so the first machine learning based proxy that I'll mention is, trained on global modeling simulations and then applied through satellite retrievals. So they, take it a step further than, we had been able to in terms of our study, where they actually have employed some of these satellite data sets in order to infer variability in OH. And so, they have sort of a similar set of variables as I, have shown here. The parameters in black are the ones that they include. And I also have tried to highlight, where our proxies differ with the red text. So they additionally include, sea surface temperature, aerosol optical depth, solar zenith angle, and latitude. They excluded the photolysis rate of ozone to O singlet D, but I think that, what they have included with some of these other terms really probably, I imagine, does a really nice job at capturing a lot of the variability that JO singlet D can otherwise offer. Okay, and I'll also mention that, that work is led by Dan Anderson, who also was, a very lovely collaborator and is a UMD alum as well, and a Goddard scientist. So I imagine there are many close collaborations with Goddard among this group. Okay, and so I'll go ahead and move on to sort of the last proxy that I'll discuss here. This work was led by someone who at the time was a PhD student at Berkeley, but now is Chindan Zhu, who's a postdoc at MIT. So, in this case, her work focused on a slightly different region. She emphasized North American cities. And her proxy similarly, is developed using global model simulations and applied using satellite retrievals. But one, nuance to that is I think she does pull in some of the model diagnostics for the development of her proxy, essentially. And in her case, she finds that formaldehyde is a more useful indicator than carbon monoxide, and also uses NO2 as in the Anderson. Okay, so here, I'm just gonna, try to give some very high level insights, offered by some of these really nice studies. And so here, this is showing the trend in OH as inferred using the proxy for the marine tropical troposphere that Anderson and colleagues had developed. And another, as I hopefully tried to emphasize with the proxy from our work, this one is also really nice in terms of being able to decompose it into individual terms to try to get a sense for what could be driving the extent of variability. So here, we can see trends in NO2 concentrations and in formaldehyde that contribute broadly to the OH trend that we see at the top. And so you can see from comparing across these figures that there are offsetting influences from NO2 and formaldehyde. We can also try to pull out a few regions where one seems to dominate, like for example in the Eastern Pacific, it seems that there's a strong influence from nitrogen dioxide, for example. So I just want to emphasize that where we're coming from is a global or at best hemispheric scale inference of OH. This project shows some really nice spatial variability in OH that is really useful and quite novel in terms of getting a better sense for how OH differs in different parts of the troposphere. Another really nice feature that the authors draw out is the relationship between these trends in the OH concentration, which again are shown on the top here, and essentially the ENSO coefficient. So we can try to get a better sense for how these climatological drivers may be affecting features of atmospheric composition via OH. So, I just have highlighted here a couple of regions where there seems to be deep convection, and that also is associated with ENSO. I think there is a mention that in these areas of deep convection that there is some uncertainty in terms of the satellite retrieval because there's often strong cloud cover in those regions too. So that could challenge things to some extent, but all that being said, I really appreciated the connection that the authors made with climatological features, which we haven't, historically been able to parse because we haven't had this sort of, sense of spatial variability in the OH concentration. Okay, and so I'm going to move on to the other proxy that I mentioned, which, again, this one, in contrast to our study and to the Anderson study, this one focuses on North American cities. And so, excuse me, here, we can see, sorry, so this plot is essentially showing the relative difference in their inferred OH concentration between 2014 and 2005. Areas where it increased are shown in red, and then where it decreased are shown in blue. So we can see sometimes it seems to me, sometimes somewhat polluted areas seem to have, more of a more of an increase in terms of the oxidant regime versus others that might be slightly cleaner. And so, I think this is really nice because it starts to get us toward thinking about these air quality connections for OH. And so the authors, tried to draw out that connection by relating this back to the ozone sensitivity regime. So here, with the example of Los Angeles, they show essentially the normalized NO2 column concentration from satellite retrievals on the x-axis, and then their normalized inference of OH based on their proxy on the y-axis. And so we can see, based on the relationship between OH and NO2, that in 2005, and which is the green line, there seemed to be some extent of indication of a VOC, or like a radical sensitivity for the ozone formation regime, whereas in more recent years, it seems that the line has flattened, which suggests they could be headed toward a transitional regime where ozone formation is more sensitive to the availability of NOx. And I think, certainly, and I imagine that the authors would agree that, I think more needs to be done to specifically demonstrate that. But, at the same time, I thought this was a really nice way to illustrate that, what we're showing here with OH has strong relevance for pressing questions in air quality as well. Okay, and then, just to sort of close and take a step back for, again, just the relevance of this work, I mentioned early on in the talk that the 2019 to 2020 increase in methane was the highest ever recorded at that time. Well, in the meantime, the 2020 to 2021 increase was even higher, and that, to this point is the highest that's ever been recorded. And so, we are still seeing, large year-over-year increases in the methane concentration. So I think, that helps to emphasize the importance of pinning down the full methane budget, including its sinks, and in particular uncertain sinks like OH. Okay, and so I have somewhat of a boring, takeaway slide here, but I just, will quickly summarize these things, hopefully give folks a chance to digest. But broadly, what I hope, was demonstrated here is that a lack of direct OH measurements affects chemistry climate model projections and can hinder methane trend attribution. Recent work uses aircraft and satellite data, physical and chemical terms related to OH to infer its variability on subhemispheric scales. And more research is needed in terms of evaluating satellite-based proxies with direct OH observations. So it'd be really awesome to have more OH observations, as I'm sure is a common takeaway of our atmospheric composition talks. More measurements are always really helpful. And also something else we may think about is trying to bridge across these the proxies that have been developed in terms of assessing, the scales or conditions for which these different formulations may be relevant. Okay, and then my very last thing that I will mention is just that we're hiring. I have this, kind of, I tried to pull, there's a cute video with Michael Regan just talking about how important it is to have clean water and clean air and, all of these, lovely natural resources that we care about. And, our mission at EPA is we care about the welfare of human health and the environment. And so if you share that goal and if you are, looking for looking for, a new opening, please consider, looking out for our announcements. Currently, my division has an opening for an air monitoring specialist, which I imagine there are some folks in this group that, would be great for that. And I will say, sometimes with these openings, other parts of our offices are able to hire, off of applications that are submitted. So it may be, even if you're interested in like more of an analysis role or like a modeling role, I would encourage you to put in an application all the same. Okay, I will go ahead and stop. So in case anyone has any questions, I'd love to hear that or any feedback you might have. Thank you.
Great job. Yay.
Thank you.
So we can open for Q&A now. So if anybody has any questions, you can go ahead and raise your hand or put them in the chat. Just ask me to, or I can't unmute you, but I can cue you. Russ, you had a question earlier. Do you want to go ahead and start us off?
Sure. Hey, wonderful stuff. I attempted to make a joke about being a lightning builder. You probably know what I'm referring to. That's your name in translated.
Oh, yes, in German. Yes. Thank you.
Maker of lightning. So a great name for an atmospheric chemist.
Thank you.
A little more seriously, as you pointed out, Dan did some, and Brian did some nice work similarly, but they didn't mess around with a photolysis rates for ozone to O singlet, which is a tricky one. So, but you did include variability in that somehow. So I was just wondering, it's temperature dependent, it's overhead ozone column dependent. How did you do it?
Yes, that's a great question that I worry I may not have a fully satisfactory answer for. So I essentially tried to communicate with the leads on the measurements for the ATOM campaign. Myself coming from very much a modeling background, I sort of, deferred to technical judgment in terms of the extent of uncertainty that folks felt was appropriate in those. And I do have a reference from Sam Hall in terms of the ATOM photolysis measurements that are available through the campaign that I certainly, can go reference, and I can also share for folks that are more interested in terms of how those uncertainty values were developed. But thanks, that's a really good question.
Okay. Yeah, it looked like an important one.
Do you have any other questions?
I will ask questions, but I really would prefer to not ask the first well, Russ did the first. We have still 33 people on board, including some people who actually work on this topic. I encourage you to engage. There will be a meet the speaker afterwards I'll talk about in a moment, but I could call on people. Okay. Going once, going twice, someone's typing, going 3 times. All right, well, I'll ask a question. So I think the holy grail here is to try to narrow the projections of the models regarding the future of OH, because they're all over the place. Part of the future of OH being all over the place is the hypothesized change in OH due to future large rises in methane that really gets me going. But my question to you is, do you foresee any pathway to using the ATOM measurements and the work that you and others are doing on the satellite data to try to sort of score the models and so we can have an informed decision about what OH might be doing in the future, as opposed to just today's world, which is, well, we don't really know what it'll do in the future?
Yeah, absolutely. For sure. I think that, our goal with this initial project was to demonstrate that we might be able to identify something that could be useful toward that, but certainly, that would be a really awesome application of what we've done here. So, some things that, I could imagine trying to follow up on, given what we found in terms of the influence of both nitric oxide in the upper troposphere and then water vapor in the mid troposphere, could be trying to look at these different models and their distributions of those two parameters, and trying to get a better sense for what sort of processes they are not representing or including in terms of those projections, how they differ, where we think we have more confidence in one or the other, and using that, I don't know how I feel about scoring it later on, but I think we could, but people can make their own judgments, right? As long as you have laid out what sorts of things you feel like you have more confidence in, or could be improved, right? So I hope that answered your question. Mm-hmm.
Yeah, it does, and I'll keep the conversation going, but I'm going to pause again and ask if there are questions from others. Okay, so trying to just make this more conversational. So, that NO in the UT, I mean, during contrast, we were so surprised to see that up there, and, throughout supposedly clean versions of the tropical UT, and we think it comes from lightning, sorry, Baublitz, but comes teasing about Russell's joke about Colleen's last name. But from biomass burning, and that is a process that I would imagine, that the uplift and the transport of that flamed wood that produces NOx, I would imagine that's very different in the models. We actually have proposed several times to NASA to study this with satellite data, but sadly our proposals haven't been selected. C'est la vie. Do you get a sense from ATOM that there's a big biomass burning component there, and is that very different in the models?
Yeah, that's a great question. So I think there was a really nice paper that came out a few years ago focused on the ATOM campaign, and that tried to pull across several models. They basically used, it's one thing that's kind of challenging is it's hard to have like a directly analogous like identification of fire plumes in terms of the observations and in the models. But with all, with whatever caveats there may be in terms of, the methods, they went on to show that the observations seem to indicate there's a much larger role for biomass burning in terms of ozone production, than the models generally represent. So, I think that was like a pretty interesting finding that came out of the ATOM work, and certainly, points to its utility there. I'll say that, for our work, we, for better or worse, chose to focus on like conditions that, well, hopefully for better for our application. I mean, we had a reason for doing it, but we chose to focus on more pristine air masses. So we actually filtered for fire plumes and hadn't necessarily taken a look at like how things, might differ with sort of more complicated chemistry.
Oh, so that figure that you had about 2/3 or 3/4 of the way through your talk, where you had like two panels and you had all that like red or orange on the right, where NO, that was filtered for fire?
I'm trying to think of what you...
Yeah.
Yes. So essentially, yeah, all of our, all of the work from the study that I had led, we had filtered for both, we attempted to identify stratospheric influence, but we had tried to filter for stratospheric influence as well as for the influence of fire, and for like really incident sun conditions.
Okay, so then maybe that is lightning NOx up there. I mean, I assume you would have used CO or HCN or something like that to filter.
Yes, yeah, I wound up using CO because it just looked, I tried to, just take sort of a qualitative look at, the tracks to see what seemed most like coherent in terms of the representation of like a fire plume. And I found, I think from, I don't know, my judgment was that it seemed like CO was a pretty good indicator.
Yeah.
Also, Rasheen Kaman, who was the CO PI for the campaign, suggested that, CO would be a good indicator too. So,
Sure. Yep.
Thanks so much for the conversation. I appreciate
More
it.
question. What's up? What's up, people? I know we have an atmospheric chemistry community here. Still at 27.
It's the first seminar of the semester. I feel like people are still warming up. It's all right.
Yeah, that's totally fine. I look forward to any conversation or other questions people might have at the 4 p.m. session too. And please don't call on anyone on my behalf. That's okay. We've had, I think, a really nice conversation here.
I've added my personal Zoom room. Well, it's the University of Maryland Zoom room to chat. So since Colleen is kindly joining us from North Carolina, I thought it would be good. Oh, wait, there's a comment rather than a question. Let's read that. Oh, okay, that's very kind. Do you see that, Colleen?
Yes, I did. I hearted it. Thank you.
Yep.
Thank you for the very nice comment.
Okay, so at 4 p.m., I will host whoever wants to join in, what we would normally do, take the speaker to coffee. I have my coffee right here. Sorry, I can't teleport it to you, Colleen. Coffee that is, not my coffee. Anyway, we're just I'll open my Zoom up for as long as people want to stay, and we'll, give Colleen a break and us a break and resume at 4 p.m. Anyone who'd like to join. I didn't send that announcement to the whole ESSEC email list. Rather, I sent it to our local atmospheric chemistry community as I know it through my own personal alias. So 4 p.m. today, my Zoom room, but there is still time for a question or two because we're only at 3:03. Anybody? Oh, Russ asked if you have a flyer on the jobs at EPA.
Oh, yes, I certainly will send you. I can, I would be very happy to send, a flyer or an email just like describing, the openings on our hiring push right now. If you all would be willing to share that, that would be awesome.
Great.
Oh, yeah, absolutely.
And for that, that last slide you had, or one of the very last slides about the job offer at EPA, at what level is that announcement for?
Yeah, so that announcement is at, I believe the 12, like a GS 12, which is generally PhD and then 1 year of experience afterward. That being said, sorry.
You finish your thought. I didn't mean to interrupt.
Oh, sure. But that being said, there are often opportunities at the PhD level, in especially the Office of Research for, in particular, postdocs. But we also have had, I also think there are many ways that, folks who are completing a PhD, especially if there was a chance they had some interim experience, can make a strong case for applying at the GS-12 level. And I've known of people who have done that and have been able to be hired directly out of their PhD at the GS-12. So if you have any students, that, might be interested, I'd be happy to chat with them as well about, maybe what to put in their cover letter.
Super. And for the ad, we didn't get the movie to play. We tried in rehearsal, but it wasn't going. Is there a contact person? Are you the contact person, or who's the contact person for the? Do you know? If you don't know, I mean, to put you on the spot.
Yeah, it should be. So for every opening, there should be like an HR contact person at the bottom of the website.
Okay.
So they probably be the most appropriate point of contact.
Do you think you could quickly, your very last, the slide with the, the video, there was a link on it, but the link won't be hot in our recording. Is there any chance you put that link in the chat?
Definitely, great idea. Thank you.
And Kazi, will we preserve these in the recording? Is the chat preserved?
It's not, but I can put all of this in I can put the video, the link, the flyer. I can put everything on the site. We can make sure that's shared.
Right. Okay. So if any students are on, and hopefully we have a lot of students on, they will take a look at the ad. And Ross asked you to say hi to Sarah Benish. I second that. How closely do you interact with Sarah?
So Sarah, was a postdoc working with Jesse Bash, who you all may know, right before I started as a postdoc, also working with Jesse Bash. And so we were, I think in very close quarters when we were doing our postdocs, and then she moved on to a nice, physical scientist position in the Office of Air Quality Planning and Standards. And I somewhat quickly after that also followed into the same office. But, now she's in a different division, and I sadly don't see her quite as much as I used to. She's more on the policy heavy side of things. But it's always delightful seeing Sarah, and she's already done some really great work at EPA in her time here.
Great. Well, say hi to her on behalf of the whole community here. We,
Will do.
one of the things that we're really proud of is that the vast majority of our students stay on in the field. Sarah at EPA, Dan and Julie, who you mentioned so kindly and prominently, in your talk today. So we're really happy to see whatever our legacy of education continue. I know Arlene feels the same way about her students. Send her a nice email about the talk today.
I appreciate that.
Okay, any
Thanks,
further
Ross.
questions? Kazi, if you want, you're fine to put this on the recording in your call.
I think that was a lovely note to finish off the seminar with. And if there's any other questions, we have it in the Zoom link. And if anybody wants the Zoom link and loses it as soon as I close this, I saved it. So Ross and I both have it. Okay, so thank you everybody for attending. Thank you so much to Dr. Baublitz for giving us this great talk and starting off our seminar series. Please join us next week, next Monday. We're every Monday from now on till Christmas, pretty much. And have a lovely rest of your day.
Okay, thanks everybody. See you at 4 o'clock in my Zoom room for the amateur chemists. Bye-bye.